Okay, so good afternoon, everyone, and welcome to this last session of QMAT for 2021. So, in this session, we'll have two invited talks. The first one of them will be presented by Professor Shouvik Dutta from IISER Pune, and the title of the presentation is Tailoring Quantum Oscillations of Excitonic Schrodinger Cat as Qubits. So, Shouvik, I will give you a reminder at about 22 minutes of your 25 minutes talk, and then
Okay.
there'll be a 5 minutes question answer session after.
Yes, sure. Okay. So let me start. The title of my talk is Tailoring Quantum Oscillations of Excitonic Schrodinger Cats at Qubits. As you can see, there are too many of the subjects are already embedded in that title. I will obviously try to explain from the very basic of what do we mean by quantum oscillations or excitons, what kind of roles excitons are playing, why we are calling it Schrodinger cats, and why do you think these kind of experimental observation can be used as qubits. The work is mainly done by two PhD students, Amit Bhunia and Mohit Kumar Singh, with almost equal level of participation. And of late, Zubrad Chaudhary, who is a MS thesis student, he is also doing some very interesting work, specifically trying to ask a lot of devil's advocate question and trying to see what else can be done with this. And I will present some of those unpublished results of Zubrad at the end if I get time. The sample that we study here is actually fabricated in the lab, molecular beam epitaxy lab of Professor Henini in University of Nottingham. However, the work, the study of these phenomena were mostly done in Indian Institute of Science, Education and Research, Pune. Now, okay, I'm not able to change my slide. Okay, fine. So what we are trying actually differently. As you know, most approaches towards quantum control or quantum computation, people tries to assemble individual qubits or quantum states into a quantum superposition state to fabricate multi-qubit, n-qubit. People, you must be knowing, Google, IBM, they're saying 53 qubit, 127 qubits, that kind of multi-qubit quantum registers. However, in this work, based on whatever our experimental observation, and I will describe it as I go along. In this work, we actually explored a top-down approach where we start with a macroscopically large quantum coherent state of millions of dipolar excitons undergoing Bose-Einstein condensation or BEC. To build these n-qubit quantum register, there is a kind of schematic given, which if time permits, I will try to fully explain. But let us begin first by the aim of our work. The aim of our work, as I said, the experimental detection and control of Schrodinger cat-like macroscopic quantum state. And these kind of macroscopically large quantum coherent state of two-component Bose-Einstein condensate of spatially indirect excitons or electron hole pairs are used as a platform. And as I have said, we are actually using a top-down approach towards quantum control. And also in our approach, I will describe the crucial role of resonant tunneling that in a quantum coupled zero-dimensional, two-dimensional semiconductor heterostructure, and how resonant tunneling in such structure actually plays a very vital role and actually tells us, gives us hint about identifying such kind of Bose-Einstein condensate state in these structure. Now, obviously, when we are dealing with a macroscopic quantum state, we get access to millions of these excitons undergoing Bose-Einstein condensation. And we will show you that although they go to one particular quantum state, but using bias, one can actually address some of these excitons independently over the other. And obviously, BEC state encounters less dissipation, less decoherences. As a result, we think it is much more amenable to quantum control. On top of that, indirect excitons can be sufficiently long-lived. We know that electron hole pair can actually recombine very quickly, but spatially indirect exciton, where electron hole pairs are located in two different layers, can be sufficiently long-lived, and as a result can be controlled even in the steady state. And obviously, as I said, in our effort to kind of experimental demonstration of quantum control will be kind of based on the experimental investigation of excitonic Bose-Einstein condensation. So obviously we have to answer, can we measure the BEC order parameter? What is the thermal de Broglie wavelength of these indirect excitons? Are these kind of the neighboring excitons are kind of coming within the thermal de Broglie wavelength or not, to give rise to this kind of condensate state? And we will show you that answers to these questions are actually affirmative, and in fact it has the potential as a result to bring the physics and technology of Bose-Einstein condensation within the realms of semiconductor chips. And in that context, I will, because it is a conference in quantum materials, I would definitely like to highlight the materials and structural requirement to achieve these objectives, and also to go forward from there. Okay, so what is excitons for people who are not familiar with it? Excitons obviously are artificial atom-like quasi-particles within solid. When one excites semiconductors either optically or electrically using forward bias, within the semiconductor structures, electron hole are created, and those electron hole face mutual Coulombic attractions and form these hydrogen-like bound state. And most of the time, these bound state have different binding energy and lifetimes based on which material you are choosing. And usually, spectroscopically, these are identified by sharp resonant peaks in the absorption spectra and all that. And mostly, so far, people study exciton by optical spectroscopy only. And another very important aspect of excitons are that they are composite bosons. Overall, they have an integer spin. And the quantum degeneracy temperature we know of Bose-Einstein condensation for bosons are inversely proportional to the effective mass of these bosons. And excitons being just an electron hole pair, you can understand that the effective mass of these excitons can be very, very small compared to, say, rubidium atom, which atomic molecular physicists actually study. So as a result, based on materials, the transition temperature for observing Bose-Einstein condensation of excitons can be quite high, can be from few Kelvin to even room temperature, based on what kind of material and structure you are dealing with. And our objective, or our experimental investigation, will focus mostly on electro-optical measurements of dipolar excitonic complexes to harness this quantum property of many-body excitonic physics. Obviously, there are definitely various results, various reports on excitonic Bose-Einstein condensation. However, there are no unique experimental signature of excitonic BEC. People study various things to be able to say that, well, in their material and structure, possibly undergoing these kind of phase transition. And we started asking the question, can only optical spectroscopy actually directly detect excitonic BEC? Because many semiconductors, like 3-5 semiconductors, the ground state based on the spin selection rule can actually be optically dark, and not necessarily they will reflect any signature by measuring light emission from these structures. However, if we understand that excitons, or as electron hole pairs, they are actually positive charge, negative charge, a kind of dipole-like quantity. And what if we try to actually probe the collective electric polarization of these excitons as some kind of probing the collective dipole moments of the excitons using capacitive measurement? And that was actually our approach from quite some years. And we have been probing excitons in 3-5 semiconductor structures, obviously dark excitons as well, because capacitive techniques doesn't distinguish between bright or dark excitons as long as they can probe the dipole moment by monitoring the collective electric polarization of these dipole moments. And let us now, so that was the kind of the background. So coming back to the sample, we are actually measuring a molecular beam epitaxy grown double barrier heterostructure samples, where within the two aluminum arsenide quantum barriers, there are many millions of indium arsenide quantum dots. And when I say that we measure capacitance, we actually measure the capacitance from between the bottom and the top contact being quite large, having diameters of 200 to 400 micron diameter. And below that, there will be millions of indium arsenide QDs. And what we do is that we use LCR meters to measure these capacitance and model our sample as some kind of a parallel combination of capacitance and conductance, and then extract by these AC measurement, we extract what will be the capacitive component and what will be the conductive component. Just to kind of give you a flavor, and in a more simplistic structure of a single barrier sample, where there is only aluminum arsenide potential barrier in the middle, we actually, as I said, we try to measure capacitance. And by measuring capacitance, we try to actually see how the electric polarization, average electric polarization of all these dipole moments of
Sorry, have I lost the connection, or is it for everyone?
Yeah, it appears. Shouvik, we cannot hear you. There's some problem.
And the presentation.
Okay, I think it kind of quickly came out of the screen.
Okay, so you
okay.
share
just,
again.
Just let me share it. Let me share it once more. Let me share it. I am not sure. I'm not able to share it. Oops.
Shouvik, do one thing. Log out of Zoom and log in. It will be okay.
Okay.
Just log out. So it will take 2 minutes. We'll wait. Shouvik, you can just close the Zoom screen and then come back in.
Okay. No, I actually closed the Zoom screen. Now I am coming back. Hopefully I will be able to display. Is it fine?
Yeah.
Are you able to see?
It is coming. Yeah. Okay. All right.
Okay. I am sorry for the thing. I may have touched something unknowingly on the keyboard. Okay. So as I was discussing here, we were discussing how we actually probe these excitonic system by probing, measuring capacitance, and through capacitance by probing the average electric polarization of these excitonic dipoles. The thing is that here, another interesting thing is that the band diagram of these kind of barrier structures are also very crucial. And it turns out that the band diagram, in the usual case, band diagrams are governed by the depletion region in a structure. However, in this case, the band diagram are mostly determined by the accumulated charge carriers around the aluminum arsenide potential barrier. And that's what actually happens in a single barrier heterostructure. Obviously, in a double barrier heterostructure that we are studying are much more complicated. And in this structure, we actually call this a 0D 2D structure, because 0D corresponds to the indium arsenide quantum dots and 2D corresponds to the gallium arsenide 2D at the junction of aluminum arsenide and gallium arsenide, where photogenerated charge carriers accumulate and create a two-dimensional electron gas. So now coming to the results, Mohammed Henini and their collaborators has also reported seeing oscillations in photocurrent in these structures way back in 2014. And then we also got these structures because we were into studying excitons using capacitance. They had sent me the samples telling, can you see what kind of excitonic features can be probed in these samples in such context. So we definitely got to see that the photocapacitance and the photoconductance both are oscillating. However, one thing can be noted that the more tunneling, the photocurrent maxima actually does not lead to accumulation of excitons, which maybe we are probing using photocapacitance. So they are not exactly at the same voltage level. And while seeing these very sharp, well-formed oscillations, which they actually explain as consecutive tunneling between energy levels of the 2-dig and energy levels of the quantum dot. But we started worrying about, because in all these cases, we are actually measuring capacitance over a very large area and having millions of these quantum dots. So we started asking questions whether this is a coherent tunneling or a sequential tunneling through millions of these quantum dots. Why tunneling through millions of such quantum dots spread over such a wide area, happening in some phase coherent way, as it seems here when we see these photocapacitance oscillations as a function of voltage. Very interesting turn actually happened when we decided that, well, let us keep our bias fixed at the maxima and minima of these photocapacitance oscillations, which are, say, minus 0.4 volt, where we see a maxima in both conductance and capacitance, and do a spectroscopy. When we do that, we see photocapacitance spectroscopy, we see very nicely split two distinct resonant-like excitonic features in that spectra. However, in the same photocapacitance spectra, if we do it with a bias at minus 0.53 volt, which is the minima of those photocapacitance oscillations, it turns out a very broad peak, and that kind of well-defined splitting between the peaks of 100 millivolt actually is vanished. However, there are obviously differences between what we see in terms of photocapacitance spectra as well as photoconductance spectra. So obviously, we also started asking the question, is this related to tunneling induced quantum coupling of these quantum dots and the 2-dig? And these kind of features are also reproduced in all these maxima, bias voltage of photocapacitance maxima, as well as all these bias voltages of photocapacitance minima. And obviously, there is one question, is that are photocapacitance and photoconductance probing to different but related physics, and why? We don't see, obviously, not much of a resonant peak like features of excitons in spectra taken at zero bias. So it kind of shows the bias driven charge carrier accumulation do play a significant role in these measurement. And obviously, it struck us to probe whether these energy splitting that we see, at the photocapacitance maximums, are these kind of related to energy splitting that can happen when two nearby quantum wells are coupled like a double quantum well potential. You know that when you bring two quantum well close by and when the coupling is maximum, the degenerate energy levels of that quantum well split. So we will come back to that and we will show you that this is possibly the case. But with that in background, we also started probing the contribution of the 2-dig in these measurement of capacitance, and we actually tried to see if the measured photocapacitance can actually be split into two parts. One is the dark and another is the quantum capacitance as a result of the screening effect of the electric field by the two-dimensional electron gas that is there in the top. And with that, because we see when we actually deconvolute our capacitance in terms of quantum capacitance, we also see that the quantum capacitance is negative. Now, quantum capacitance is usually defined as derivative of the chemical potential with respect to the number of charges. Now, if that is negative, obviously the next question comes is related to in-plane electronic correlation. Usually the chemical potential of excitons is actually decreased whenever there is a formation of excitons, because the binding energy actually reduces the chemical potential of excitons. And so in a way, we tried to actually explain whether negative quantum capacitance that you see is leading to in-plane Coulomb correlation. And we know that can actually happen because the holes that is kind of there in the indium arsenide quantum dots can attract the electrons in the 2D. As a result, some of these electrons can actually get captured as an exciton by these quantum dots. As a result, over the XY plane, there can be some correlation not only between the electrons of these 2D, but also between the excitons. And that can come from the repulsion, the repulsion between the electrons as well as the excitons in that scenario. So in that context, we then ask actually, is the negative quantum capacitance is actually related also to the in-plane electronic correlations, which may be driving these excitonic system towards Bose-Einstein condensation. Obviously, one has to check whether this is temperature dependent, and it seems that the magnitude of the photocapacitance and photoconductance, these oscillations are kind of begins to appear only below certain temperature of 80 to 100 Kelvin. Although the magnitude are kind of increasing like a phase transition below these 80 to 100 Kelvin temperature, you must actually also understand that it is not just the fact that excitons, number of excitons are increasing at low temperature, because if you look, we know that capacitance is probing the effective polarization of these excitonic dipoles, and that not only increases but actually decreases, in a way oscillate around certain value. So we know that these are some kind of a phenomena which we kind of see. Usually capacitance of any semiconductor samples freezes as you go to lower and lower temperature. So this is definitely something very interesting.
So Shouvik, I just wanted to tell you that you have 3 minutes of your 25 minutes.
Yes, I will try to very quickly do it. So, so what is the connection between these? It seems that as the excitons form, and if the BEC if the quantum capacitance, negative quantum capacitance drive these excitonic systems towards kind of aligning the average electric polarization along the direction of applied bias, there may be some localization of these electrons which may be driving the BEC. And because we are seeing very, very sharp oscillatory features in these photocapacitance measurement, it turns out that such kind of localization of these electrons can only happen if put some restrictions on the in-plane wave vectors or the kinetic energy of these electrons in the plane of the sample. And that can certainly point towards the fact that these electrons or excitons can go towards a state where the transverse component of their momentum can be severely restricted. And if that doesn't happen, any random phases during any sequential incoherent tunneling through millions of such quantum dots can be averaged out, these oscillations measured over such a large area. We also calculated what is the thermal de Broglie wavelength of these excitons around such temperatures, and that wavelength is certainly much larger than the spacing between the excitons which are localized in these quantum dot system. So we know more or less that also satisfies. Now, if it is an excitonic BEC, whether we also see some off diagonal long range order. So what we see did is that we tried to measure oscillations with two different lasers, and then simultaneously as a result, what we see is very interesting, is that it seems, although these laser spots are macroscopic, covering nearly 200 microns of area, but when you actually excite them with both the lasers, the oscillatory changes in photocapacitance at simultaneous photoexcitation intensities are certainly much larger than the simple algebraic sum of photocapacitance of the individual laser beams. Once you actually subtract the background, that's kind of indicating phase coherent interference of excitons over a macroscopically large area. People can say, well, these phase coherents may be coming from the lasers, but we have done the same experiment recently, even with white light and a laser, and white light is not a coherent light. So it clearly indicates that whatever phase coherence we are seeing, which are leading to such kind of beat patterns, are actually being generated within the solid and not coming from the photoexcitation source. So just quickly telling you some very interesting result is that we again thought of sitting at the bias voltages of these maxima and minima and then try to vary the light intensity. This result is still unpublished. We have actually overlooked the behavior of photocurrent for a quite long time. It seems once we are sitting at one particular bias voltage, that is pinning the energy levels, and there is no oscillations in the photocurrent. But if you look at the behavior of both photogenerated capacitance and photoconductance, you see very interesting oscillations. In fact, the minus 2.04 and minus 2.19 are actually one of those oscillation maxima and oscillation minima. And once you sit there at one particular voltage and just vary the light intensity, you begin to see these very nice oscillations, which we think that if the energy levels are actually strongly pinned, then and there is no oscillations in the photocurrent, so it clearly shows that there is no sequential energy matching which is leading to such kind of oscillation. And looking back at whatever results people did earlier with single QD, we can now kind of say that these kind of oscillations are possibly the phase coherent Rabi oscillation measured over millions of quantum dots. I will skip many slides. Again, I will tell you that this kind of spectral splitting that I have discussed in the beginning can actually be explained as some kind of a Hadamard gate operation when two neighboring quantum wells, one is indium arsenide quantum dots, another is gallium arsenide 2-DEG. They are kind of quantum coupled, and we know, just like a coupled oscillator model, when two oscillators kind of get coupled, there is a splitting of energy, and we try to actually understand these in terms of that. Well, why macroscopic? It turns out the average electric polarization, which can be written in a quantum mechanical terms as trace of average, a trace of electric polarization and the density matrix, can actually probe many particle
3 minutes
quantum
of
correlation.
Your total 30 minutes time. Okay, you have 3 minutes out of
so
total 30 minutes.
So we kind of
Q&A.
demonstrated. Yes, we kind of demonstrated that these kind of quantum control can be done, and well, I will obviously many more work is going on whether to see these things in time domain and all these other things. I will skip all of them. We have also did some calculations to prove that quantum coherence actually sustained in these resonant tunneling. So in a way, I will just directly go to the final slide, which says that, well, we have seen this at 10 to 100 Kelvin temperatures. However, operational temperature can certainly be raised with more densely packed ordered arrays of QDs or materials having larger excitonic binding energy. And that possibly will be my request to my friends in quantum matters, that I know fabrications of single crystal of these 0D 2D heterostructure using these 2D materials, trendy 2D materials of TMDC, oxide or perovskite can be quite difficult. But if some of them can actually fabricate these, we will be very happy to study these materials, exactly for the reason that it can be possibly scaled up at room temperature as well. Even at this stage, nitride semiconductors having higher excitonic binding energy can be used. So we think our work can lead to faster and wider adaptation of quantum technologies in terms of miniaturization and portability by using semiconductor nanostructure. So I'm sorry I possibly took some extra time just because we got disconnected in between. And thank you. If there is any question, I will be happy to answer.
Okay, thank you, Shouvik, for your presentation. So floor is now open for question answer session, but because of the shortage of time, maybe we'll limit the quick question like one or two. Okay, so I see Pratap raise your hands. Pratap, could you please ask your question to Shouvik?
So, Shouvik, if I understood it correctly, the
Yeah.
increase of the capacitance E was what at low temperature was the signature of what you claim to be Bose-Einstein condensation.
I mean, that's definitely happening, that that is increasing, but we have also calculated the de Broglie wavelength, and it is much larger. Even at those temperatures of 100 Kelvin, you can see the de Broglie wavelength is much larger than the spacing between the excitons. So as a result, it kind of shows that the Bose-Einstein condensation should take place. Why it should not take place when the de Broglie wavelength around that temperature is pretty large compared to the those indirect excitons, which are kind of anchored with those quantum dots.
Okay. All right. I had many other questions, but I won't ask now.
You can email me and we can discuss again. No problem.
And then there are the breakout rooms where you can always go and have discussions.
Yes. Sure.
After this talk.
Yeah. I'm sorry. I think something got disconnected during that.
No, that's okay. So this can always happen with anyone. So, but let us now move to the next talk. If there is no more questions, and I don't see any further raised hand, so let us thank Shouvik for his presentation, and let us invite our next speaker, Professor S Anilkumar from IISC Bangalore, to present his talk entitled "Investigations of Weak Topological Insulators." So, Professor Anilkumar.
Thank you. Are you able to see my slide?
Yes, we can.
Thank you. First of all, let me thank the organizers, Professor Sangeeta Bose and others, for inviting me for this lecture in this conference. It's an exciting conference. So today, this is the last lecture in this series. So I'll be talking about weak topological insulators. So I will introduce what this weak topological insulator is, and how do we do, certain experiments in this kind of topological insulators, and what do we expect and what do we want to do in future. So this work is carried out primarily by, today's work which I'm going to present is primarily carried out by Kunjalata Maji. She was a PhD student here. And then this work was continued by Shouvik Mandal and Debargia Malik. Both did on slightly different system, but all three worked on weak topological insulators, and my collaborator, Dr. Ganeshan, in the department. And I also would like to thank Professor Viju Shekhar from IOP Bhubaneswar and Professor Umesh Vakmare from JNC for the angular salt photoemission spectroscopy, as well as the theory inputs to this work. And as usual, the funding from Nanomission DST and the National Nanofabrication Center at Indian Institute of Science. So in the morning also, we have listened to some talks where topological insulators were briefly discussed. So just for some students who are not familiar with this topological insulator is a new kind of a material where in the bulk, it's like an ordinary semiconductor, but the surface hosts protected metallic surface state. And today morning, we saw a lecture where this kind of a band structure was shown, and what is the origin of this surface state is seen. And this is the point which is called the Dirac point in this system. And then not only that, if you look at the 2D surface state on the surface, you see that the electrons with a particular spin direction moves only in one direction because of this peculiar band structure. So that means if this electron is moving towards the right, and unless this electron encounters a magnetic impurity, it cannot scatter back, because if it has to scatter back, then the spin should be changed. So for spin angular momentum to change, you need generally a magnetic impurity. So this says that unless there are magnetic impurities in the system, you can get a very good spin polarized electron source. And my interest in this kind of system is due to the possibility of getting a spin polarized electron source here. But these systems are very, very exotic. And this topological insulator, I'm just going to the next variety of this. Is this top thing obstructing? So what we are going to talk about is a new class of material which is called a weak topological insulator. Very soon I'll tell you what this weak topological insulator is. So this is about a weak topological insulator. So the weak topological insulator can be thought about a two-dimensional quantum spinol layers stacked together. And then what happens if you take this stacking together, you will have topologically protected surface states only at the side surfaces, whereas the top surface is a dark state. That means there's no metallic surface state at the top and bottom surfaces. But on the side surfaces, you have this topologically protected state. And it has been shown that you have even number of Dirac cones on the side surface. One of the classic examples for such a material is this bismuth rhodium iodide, which was shown both theoretically and experimentally that it is a weak topological insulator. So what distinguishes a weak topological insulator from a strong one is this Z2 invariant, where this Z2 starts with 0:1001, where this 0 indicates that this is a weak topological insulator. And when this Z2 invariant mu0 is 1, then it's a strong topological insulator. But if you look at this system, though this was predicted, or realized way back in 2013, but the electrical properties of this system is not well studied because of inherent difficulty of making the system and then looking at the properties. So in this process, we came up with a new weak topological insulator. Actually, when we made this, we didn't know that this is a weak topological insulator. Then the theoretical calculations of Professor Umesh Wakmare pointed out that this is a weak topological insulator. So now let me just tell you what is the structure of this weak topological insulator. So we are all familiar with Bi2AC3 topological insulator. So here what we have, two bilayers of Bi2AC3 and a bismuth bilayer. So that means the structure is that two Bi2AC3 layers coupled by a bismuth bilayer, so that the unit cell goes to around 23 angstroms. So this is a simple BiAC. So Bi2AC3 plus Bi2AC3 plus 2Bi, that forms the structure of this material. And this is a very interesting material. Now this we grew these materials by Bridgman technique. And then, it takes around 15 days to grow one crystal. So we have to do several trial and errors to get a proper good crystal. And this is the example of the X-ray diffraction of this material. This says all the 00L orientations here. We also did high resolution transmission electron microscopy as well as Laway diffraction to find out the single crystal nature of this material. So once we have this kind of a single crystal, then we do a lot of studies with this. We did, see this slide, I'm just flashing this slide just to tell you about what is the important aspect. The theory that is generated by Umesh Wakmare or predicted by Professor Umesh Wakmare shows that it is a weak topological insulator, and the band structure which he has obtained, and we have confirmed with the help of Professor Biju Rajshekar with our angle dissolved photoemission spectroscopy, just to give you a convincing evidence that this is a weak topological insulator. So now we are interested in the electrical properties of weak topological insulators. So that is why we start making the devices out of this single crystal. So what we do, we exfoliate these crystals like what you exfoliate graphene. You can exfoliate different kinds of layers, and we can also cover it with hexagonal boron nitrate for protection. So what we do, you take a glass slide and coat PDMS, and then you make with a scotch tape, you get HBN on one side, on another silicon dioxide substrate, you get your material, and then under a microscope, you bring them close to each other, then apply the right temperature so that it is released and the structure is formed. So this is all done, including the exfoliation and the device fabrication. Everything is done in a glove box with extremely good conditions so that the moisture and the oxygen is brought to a minimum level. So once we have this devices made, so what we do, we have this process. So we have the single crystal, exfoliate it, and then the exfoliation is done, and then you do the AFM to find out the thicknesses, etc. Then we do the electron beam lithography. Then you do the metallization contacts, etc. Then you do the wire bonding, and then you get it into the chip carrier and do the wire bonding. So this is the device that will go into the cryostat for the electrical transport studies. Now comes the interesting properties. Once we have all these devices made, we look at the electrical transport. Here, the first experiment, what we do is that you have a device like this. You measure the resistance of this sample as a function of temperature. And what we found was it is a metallic, it shows a metallic nature. So ideally what I wanted was an insulating behavior, like, we do three-dimensional topological insulators where we do compensation doping and we get an insulating behavior up to a certain temperature. And then we have this metallic surface states taking up. So we wanted something like that, but unfortunately, though I said that the bulk is insulating and the surface is metallic, but here what happens is that the bulk is also kind of conducting because of the self-doping, because of this deficiency of selenium in the sample. So, but nevertheless, we have this crystal, let us understand. So it gives, because of the self-doping, it gives very high carrier concentration and the mobility is of the order of 520. So that we obtain from the Hall effect measurement in these samples. So then we try to establish the electrical properties of this material. We do a magnetoresistance measurements, and then we get something called weak anti-localization. So this weak anti-localization was generally in this community is fitted with an equation called HLN equation. So with this HLN equation fit, you get very interesting parameters. How do I take this? So very interesting parameters like the coherence length of this material and alpha, which gives an indication about the number of conducting channels in the system. So usually in a three-dimensional topological insulator, if you have a crystal and if you have a top surface state and a bottom surface state, if you measure the weak anti-localization and look at this alpha value, it will be 1. That tells that you have two different surface states. So we extracted the alpha value. The alpha value is approximately 1, and we can also get the L5, which is a coherence length from this fittings. And the coherence length also we can measure at different temperatures. Sorry, this is temperature. At different temperatures, then you can fit it with this equation, and you can extract the parameter gamma. So the gamma equal to 0.5 says that it is a typical 2D system. And if gamma equal to 0.75, you will see a three-dimensional system. So now, so far, we have a crystal, and the angle solved photoemission spectroscopy was matching with the theoretical predictions, and the theory says it's a weak topological insulator. So far, we can say that, look, it's a weak topological insulator, and it shows kind of a 2D transport in the system. And that is a conclusion that we have up to this point of time. So then we started asking the question, apart from the single crystal, can we also grow the epitaxial films of this kind of materials? So what we do pulse laser deposition to deposit BISE films on silicon 111 substrate. And we can see that, you can vary different parameters in the laser. And this, I'm just telling you one set of parameter that we varied is the temperature of the substrate. So you vary at different substrate temperatures, you grow the films. And finally, around this temperature, we get approximately a good quality films. So we also do the atomic force microscopy analysis to get about the quality of the film. And this has a correlation with the other properties which we are getting, which I'm not going to discuss here. So an important parameter that we use to quantify the quality of the film is Raman spectroscopy. So the topmost spectrum tells the Raman spectroscopy from the single crystal, which I was showing you earlier. So we get this Raman spectra like this. And if you look at the surface temperature, when you grow the thin films, you get a spectra like this. And as you increase the substrate temperature, you see that around 300 to 325, this Raman spectra matches exactly with what is the Raman spectra of a single crystal. So that tells us that, you know, the quality of the BISC film is acceptable. So now we have a choice of varying the thickness of this the BISC films and start looking at the transport properties. We can go, I mean, we have studied between 9 nanometers to 70 nanometer of BISC film. And then we have also looked at the Hall data, and we see that the carrier concentration that we are getting in this BISC is comparable to the carrier concentration that we were getting in the bulk material. And but the mobility of the system has gone down. But that's not the important aspect here. I just wanted to prove that no, this also shows the exactly same electrical property as that of a bulk crystal. So if you look at the 25 nanometer film here, again, you can fit it with this weak anti-localized, this HLN equation. And this is the experimental data and the fit to this equation. From this, we extract the parameters like L5 and alpha for this system. Now for different thicknesses of this film. So now if you look at the alpha and L5, we see that when you make the thickness extremely small, like say 9 nanometer, this alpha is going to be 0.5. That tells me that the surface states are all interacting with each other, and you get a single channel of conduction. But if I increase the thickness above a certain point, that you see decoupled surface states here. Similarly, if you look at the temperature dependence of your phase coherence length, you see that for low thicknesses, it follows approximately 2D behavior with this gamma value coming close to 0.5. And as you go to higher thicknesses, then it's moving towards a 3D transport. So this all happening because the system is also a little bit self-doped. So now with this understanding, we now started asking the question, when we work with strong topological insulators, what we do, the strong topological insulators like Bi2AC3 is also self-doped. So in order to compensate for that, we are doping with, instead of bismuth, we add antimony, and instead of selenium, we add tellurium to get the compensation doping so that we get a bulk insulating material. So we also started looking at the chemical doping of this material, and we dope with different materials. And in this particular remaining few minutes, I will show the results that is coming from 8% antimony doped bismuth selenide. So it is the antimony doping, and again, all these crystals take quite a long time. So we should appreciate the patience of the students. Each crystal takes around 15 days to grow. At the end of the 15th day, you realize whether you have to throw out this crystal or you have to use it. So finally, after all these things, and Kunchalada got a very good crystal like BISC 0.08 antimony. So again, though we wanted to have a insulating bulk, but still we are not getting the insulating bulk. But you will see soon that the carrier concentration has come down. We are continuously improving the properties. And at the same time, we are also growing other crystals like BITE, etc. But now if I look at the magnetotransport of this material, you see that if I measure the resistance as a function of applied magnetic field, you see that above a particular field, you start seeing nice oscillations. And on either side, you see very nice oscillations. So you can appropriately remove the background. So once you start removing the background, you see this Shubnikov-de-Haas oscillations in this material. So this tells sometimes about the quality of the material. You get nice oscillations starting from 3 Tesla, and in the temperature range 2 to 8 Kelvin, you get the oscillations. So now, once we have these oscillations, we can extract several parameters about the system, which is unknown in the past. So the first thing is that we'll have to understand the SDH oscillation. So henceforth, I will just call this as SDH oscillations. So we have done it at different temperatures. And first of all, you can do a fast Fourier transform, and then you get this the field, the frequency, which is coming 66.7. And if you plot, if you analyze the amplitude of this frequency as a function of temperature, you can talk about the effective mass of the charge carriers in the system. So if you do a proper analysis, and we are getting effective mass of this charge carriers as 0.14. So this is one result that we are getting. I just wanted to remind you that this kind of studies we do on multiple crystals and multiple samples, and finally all those samples we get almost identical values. So this is just to tell you about the reproducibility. Now again, these oscillations we can also analyze by different methods suggested by different people. See, for example, we can have a Lifshitz-Kossovich formula, and you can do the analysis of this oscillations with that, and we can extract the Berry phase in this material. And what we are getting in this particular system, putting all the approximations that is important for this system, we get a Berry phase approximately pi. So, if I have this, error bars added to it, then you will see that it is approximately pi. So you are getting a pi Berry phase. So the pi Berry phase is also giving you a indication that you have Dirac electrons in the system. So it's a two-dimensional nature of transport and the Dirac electrons in the system with an effective mass which is 0.14 kind of thing. So then you can further do analysis. You can do a Landau level indexing, and the fan diagram can be constructed. You see that these are the different oscillations. We index them like 9th, 10th, 11th, 12th, 13th Landau level, and then we can plot this 1 upon applied magnetic field versus this Landau level index. And then you get a very nice straight line. If you look at the straight line here, if you fit it, that will also give you the same frequency which we have extracted earlier, which is here it is 67.58, which is approximately 0.58 Tesla from the FFT that we were using. So it is all giving you very conclusive results. Now, if you extrapolate this and you see that this is giving you an intercept of 0.47, and this 0.5, if the intercept is 0.5, then it tells that you have pi Berry phase. So this also tells you that you have a pi Berry phase in the system. So this all data which gives you information that it is 2D Dirac fermions in the system. So this is the first time that in a weak topological insulator, we are getting such kind of information. Another interesting analysis that we can do is something called a Dingle plot analysis. So if you take this particular, you convert your resistance into this particular form and then plot it against the inverse of the field, then from this plot, you can get something called a Dingle temperature. So the Dingle temperature is a temperature that people, the Dingle has used to reconcile between the theoretical predictions of Landau and this de-Haas-Swan oscillations coming there. So this Dingle temperature also gives you a lot of information about the system, about the lifetime, etc.
Professor Kumar, I just thought to remind you that you have 3 minutes left out of 25 minutes of it.
Yes, I'm done already. So the last slide, I just wanted to give you very important information that now if I look at the Hall data of this system, this crystal, 8% antimony doped IISC. So you get a nonlinear Hall data, and this nonlinear Hall data can be fitted with the two types of carriers. And now what we are getting is that if I look at the mobility of the charge carriers here, this mobility has gone. If you remember correctly, when I showed you the single crystal that had around 500 mobility, that has grown up to 15,000 mobility of 15,000. There's a giant increase in the mobility of the system. And this increase in the mobility was responsible for you to get that quantum oscillations, those oscillations. And from there, we could extract many parameters of this system. So this is a very, very wonderful and interesting system, not explored much. There are many more things to be understood in this kind of systems. So I just wanted to conclude that, this topological insulators are a very interesting class of materials. And we extensively work on 3D topological insulators, the strong topological insulators. And now this is another area which we are exploring, which is a weak topological insulator, which is relatively less understood and less studied. And we are trying to understand the physics behind all these things. And we also found that, if you start doping, say, for example, we got 8% doping of antimony into this via bismuth selenide. We started getting this Shouvik oscillations, and that gave us a lot of important information that you have pi Bailey phase in the system, and also we could also enhance the mobility of the system to around 15,000. We keep on increasing, trying to increase the mobility. So now we are also working towards doing further doping at different sites to make sure that the carrier concentration comes even further down, so that you get the proper bulk insulating material as well. And we are exploring both thin films as well as single crystals for this study. So let me thank you for your attention. This is my group which was taken pre-corona in front of the physics department of IISC. Thank you for your attention.
Okay, thank you, Professor Kumar, for your nice presentation. And the floor is now open for questions. So I will try to see raised hands. Okay, so is there a question that audience would like to ask Professor Kumar?
Yeah, hi, Anil, this is Chiranjeev. Just had a question. You said that you made a film of 9 nanometers. So was it like smooth, or you had sort of island kind of good, like it had completely covered the surface?
Yeah, it is covered the surface, because when you do the electrical transport, first of all, you get nice continuity. And also when you do the AFM, there is a background on which you get this triangular shaped things are coming, but the film is continuous.
Yeah, thanks.
Yeah, so I don't know, can I sort of ask or just a comment?
Sure.
Yeah.
I mean,
yeah. Thanks for a very nice talk. So yeah, so just a comment that because you have all the analysis, so it would be nice to compare perhaps the quantum scattering time with the scattering time which you get from transport in the mobility, because you already, so have you sort of compared those?
Yes, it is compared, and see if my memory is correct. This mobility was slightly lower in one of the cases. I don't remember exactly. I did not capture those numbers here. There was a slight deviation in the total mobility of the material.
Yes, so that's of course to be expected, because or should it be the other way around? The quantum scattering time should be sort of smaller than the other one, no? Or
yeah, that's what I don't remember the exact numbers. There was a slight deviation.
Okay, thanks.
Okay, is there any more question? I'm trying to see through the list and looking for raised hands. I probably don't see any more. But let me ask a very naive question, Professor Kumar. That is, so what exactly are the advantages of this weak topological insulator over the other ones for the devices, for fabricating devices? Are there any, or?
Not that I can tell you that there is an obvious advantage or a disadvantage. The thing is that in the strong topological insulator, see, here we need to understand, ideally speaking, my top surface should not have given me a surface state, but I'm getting it. So if you look at some theory that has come in the last couple of years, that the top surface is not a continuous surface. There are steps at the surface. So you have those edge states, and which they call it as a hinge state. That hinge state is responsible for this topological transport in this material. So in the case of a strong topological insulator, we were successful in doping it correctly to get a bulk insulating material where you could make p-type, n-type by electrostatic gating and all those kind of things. And we also made, we showed indications of topological superconductivity at the interface between these two. So I'm just thinking that this kind of weak topological insulators may be useful in that respect if I club it with a superconductor like niobium selenide, like because of this hinge states are responsible, maybe we will get that kind of a one-dimensional superconductivity. So apart from that, from the application point of view, I have no answer to your question. I don't know whether there is an advantage or a disadvantage. It's a new class of material, and we are trying to extract the physics out of it at this point of time.
Sure, thank you. So yeah, certainly you have characterized the material quite extensively. Okay, so if there is no more question, let us thank Professor Kumar once again, and then let us thank both the speakers of this session. And with that, we formally close this session, and I would request organizers to take over, because I think there is one further session which is not really talks, which is supposed to start on this particular link only. So anyway.
Okay. Thank you, Amit, for chairing the session. And I thank both the speakers for excellent presentations. So this Zoom session will continue. We'll have the concluding session. So I am trying to find out whether session 2 has ended. So please don't log out. If you want to quickly grab a tea or whatever, you can get it. But please come back, because we will have the concluding session on this Zoom session, say in 5 minutes.
Hi Pratap, session 2 ended. So people will-
Hi, Pratap, session 2. Yeah, and we have asked all of them to come over here. So maybe wait for 1 more minute and then we can start here.
Okay, Rasdeep, so
Yeah.
has the session ended, session 2?
Yes, session 2 has ended. So yeah.
I see.
And we have asked people to join here. So yeah, we came from there. So yeah, maybe we can start the session here.
Okay. Okay, so we come to the end of this of QMAT 2021. I think for me as the organizers, and I think for all my co-organizers, this has been an extremely satisfying experience. The enthusiasm of the community for this conference is indeed extremely rewarding. So we wanted these to become a community meeting when we started 4 years back. And I think over these years, it has actually taken that character. And this is actually something that is extremely gratifying. Okay, so we will take your feedback and we'll announce the next year's conference. And I think for this session, let me invite Rasdeep to conduct it.
Thank you, Pratap. I was just remembering the one night in ICTS where me, Pratap, Krishnendu, and Gautam first said we should have such a meeting, and then from that it has been a long journey for 4th installation being completed. Let me start with the good news first, and then gradually go on to tech feedback and everything else. Maybe I'll first like to thank a few people. So because such an organization, although you have seen me and Pratap a lot more than others, but this of course is not just a 1-person or 2-person job. So I'll first like to thank the members of the organizing committee this year. It was people from TIFR other than me and Pratap were Vikram Tripathi, Shouvik Chatterjee, and Thamizabel. And then there were from CEBS, Sangeeta Bose, from BARC, Debjani Kormakar, and from IIT Bombay, Shommo Bera and Abradeep Pal. They had worked very hard behind the scenes to make this happen. I would organizing, I mean, we are not that tech savvy. We are kind of the older generation. So all the technical aspects of this conference, including Zoom, the virtual reality part, frames, etc., has been managed mostly by the students and by 2 of our technical team coordinators. So I would like to specially thank Mr. Ajay Salve and Mr. Kapil Khariali of the Department of Theoretical Physics, who were, there. They were coming here at 8:30 to start our sessions and were being here till the end of this and so on. And they did a lot of work behind the scenes. Amongst the students, Sharonno Moitro and Nunmesh Ghorai from the Department of Theoretical Physics. They were the main sort of brigade behind, I mean, they were leading the brigade who were doing all of this work behind the scenes, also Mursalin Islam. And there was a lot of people who were involved in the frames and other virtual behind the scenes technical aspects. So I would like to thank all of them. I'd like to thank TIFR for providing us a generous grant to hold this conference, which covered some of the costs. Also to IOP Publishing for their grant and sponsorship of part of the conference. And I would also like to thank Mr. Devendra Buddhikot, who is from Department of Condensed Matter Physics and has been hosting the whole website from very long time. Also, my personal thanks to Krishnendu, because I have been talking to him behind the scenes quite a lot to make things like this happen. So that's, I think that's a whole series of people that we wanted to thank. Now, let's go to the, okay, this one is almost over. So we should plan for the next one. And I am very, very happy to announce that the next QMAT will be held in IIT Kanpur, and it will be held in hybrid mode. So the people from IIT Kanpur has agreed to host the next meeting. And I see Arijit is there from IIT Kanpur. So maybe Arijit, you would like to say something?
So we are extremely privileged to have such an opportunity to not only organize a meeting, also to meet many of you personally, which is the connection we missed for last now couple of years. Yeah, so we really look forward to have a good part of you physically present in IIT Kanpur. I hope it will be also a nice experience for all of you. Yeah, so we are still figuring out the logistic of things.
Yeah. Okay. So maybe before we go for the feedbacks, maybe we people can switch on their cameras a little bit so that we can take what is nowadays called the conference photograph, which is essentially a screenshot of your Zoom screen.
Yeah, this is what I have been doing. I've taken a few.
Yeah, if everybody can turn on their screen video, it could be very nice.
Let me see. Everyone possibly will not come on one screen, so I'll have.
No, there'll be 3 screens. I can see 3. Even if you see in gallery, there'll be 3.
So I'm taking the. So just be a little patient. I'll have to take 3 screenshots.
Pratap, are you done?
That is done. That is done.
Okay, you wanted to say something. You had raised your hand. Yeah.
Okay. So I just want to say one thing, that it may be known to those who have attended this conference before, but for those who are joining this conference for the first time, so we adopt a policy in this conference that no speaker speaks on consecutive years. So if you speak on 1 year, you don't speak the next year, you might be speaking the year after that. And that is the way, that is the only way we can see that even with that, we had 70 invited talks this time and 34 oral presentations. So that's the only way we can rope in this growing community within this fold of the conference. So, however, we would definitely like everyone to participate every year, and irrespective of whether they are talking or not. And this online mode has, of course, given us a fantastic opportunity. The hybrid mode will be the best of both worlds. There will be sufficient opportunity to physically meet among a section of the colleagues, but those who are not able to come can also attend with full participation, not just listen to the lecture, but with full participation online. So I think from this year onwards, it's almost evident that we will never go back to the full offline mode. If if pandemic situation is good, we'll definitely adopt hybrid. If it becomes really dire, we will go online. So that's just a clarification for that I wanted to give before we go for the feedback session.
Okay, thank you, Pratap. So now we come to the part where we would like you to give us some feedback, maybe things that you like, things that you didn't like, things you think can be improved or changed. So please raise your hand and I will go one by one. So I see already Amit has raised his hand. So Amit, please
so
go ahead.
this is not a feedback. This is a quick question. When exactly will the QMAT 5 take place? Have you decided the time?
Second week of December.
Second week.
First or second week of December. Orijit, that's right.
Yeah. So essentially, it is constrained by the end of the semester. Once the semester is over, then we will have the availability of the hostels. So it's probably going to be either first week or second week of December, which is a nice in terms of weather in country. I would say,
yeah. Okay. Anyone else has comments, feedback? You can raise your hand and I'll be looking for raised hands to go along.
Okay. So there is something Vijay wants to ask.
Yeah.
Okay, so Vijay, let me answer for Vijay. Vijay made a point that I think we should reserve few invited talks for students and postdocs. Maybe it can be by selection procedure. Okay, this is something we can discuss, but the policy that we have adopted this year, let me just tell it that we have tried to do as much consultative, we have tried to operate in as much consultative mode as possible. So for the oral presentation, there was a mail that was sent to a huge mailing list. Actually, the mailing list is the mailing list of QMat last year, plus the mailing list that I got from Manoranjan Kumar, which is for one of their Bosch colloquium which they arranged. And that is sent to a huge number of people. So there we had asked for suggestions for bright young people whom senior colleagues feel that should give a oral presentation. And this is how we made the list. And in fact, we have taken all the suggestions. We haven't, this year, the number of suggestions that we have gotten was of the order of 27, 28. And in addition, we had put some others, particularly postdocs, we have always given priority. So even if there was no explicit recommendation by anyone, we checked all the postdoc abstracts and tried to accommodate most of them in the oral presentation category. Now, in the long talk category, this is something we can discuss whether. But it's a matter of accommodating as many as possible. Krishnendu, you have something to say, I think.
Yeah. Just sorry, Sindra. Okay. So the thing that I wanted to say was that the only thing is that it would be nice if this could be done on 4 weekdays rather than having a Saturday included, because as I saw, I mean, it's not just me getting up from the bed and going to office at 8 in the morning, but that's not the point. The point is that, so the second session today didn't pick up that many people, right? I mean, and this is bound to happen if it is on Saturday or Sunday or weekends like that. So in case it's possible, it's not, it's nothing earth-shattering, but in case it's possible, probably better to do it on weekdays so that there is a uniform distribution of, talks on every day. And so that's the only suggestion.
Yeah, in fact, there's a That's probably true. And the weird thing was initially when we were fixing the days, we were kind of hoping that we could have a hybrid mode this year. And the Friday and Saturday was kept that people may be able to travel. So it turned around when it became completely online, but we were at that point hoping that maybe, some people would be able to come, and keeping a Friday and a Saturday would be useful in that respect. But I agree with you. If it's completely online, it's better to have it on weekdays. Yeah. Any other comments, questions, queries?
We haven't heard anything from students and
any of the students
participants. If you have anything to say, please feel free. Shourav, you have something to say?
Shourav, you.
Actually, I have something to say related to this poster presentation mode. Although it means it is very good, but somehow we found that there are some eco issue and many things was happening. So if somehow it can be resolved further, then from next session, means next year, this poster presentation can run in a smooth way. Because this year there was lots of issue, but now it depends upon how can we make a good platform, or even this platform itself, it can be improved or not.
I see. So what you do is that our email will remain active. Whatever issues were there, you just write to us.
Okay.
We'll pass it on to the organization or organizers for next year, and to the best we can, we'll try to address them.
Yes.
So for us, using this mode for poster presentation is also a new experiment. We have never done it before. So everything may not be, and also we have used frames. There are also other platforms that are gradually coming up.
Yeah.
Frames is the cheapest of them. It's not
actually I found the frame that although it might be the cheapest, but the thing is that it seems quite good. Means when you are roaming around there in the frame option, it was at least it feels quite better than the other platform which I have attended, like in Slack or another one. So, but in that respect, the frames was very good.
Okay, so send us your suggestions.
Yeah, sure.
Whatever suggestion you have, the problems that you faced, you mention that, and then if you also come across better platforms, also mention that. So it may be that we are not aware of all the possible platforms. We will explore. If it is exorbitant, then we may not. Actually, one thing that I would like to tell everyone, because here there is a large fraction of the community here, as you have seen, this year there was no registration fee at all, and the total expenditure was actually quite small because it was in the full online mode. So in fact, to give you an idea, the expenditure this year is of the order of 35,000. However, if we go for hybrid mode next year, we need to put a registration fee. How much is the registration fee will depend on how much money one can raise from other sources, both governmental and non-governmental. So please keep that in mind, that when it is in a hybrid mode, there will be a registration fee, which will definitely be within a limit that most of us can afford.
Okay. Any other questions, comments? We had some young colleagues from outside India who were, anyone wants to comment from them? Any of the students? Okay.
So I had only one wish, which Pratap sir already mentioned. So if some kind of online broadcasting is available for the next years, so it would be very much beneficial for us so that we can attend it from outside India. But you already mentioned that will be the case, so I am happy.
Okay. Yeah, I don't think, and we are from now, it's very hard for conferences to go into completely offline mode.
Yeah.
Simply the access is too big to let it go.
Yeah.
Would be my general thinking. Okay.
So I noticed that there were 2 participants who attended almost many sessions who were not presenters. One is Professor Rustagi and the second one was HRK. Do you have any comments or suggestions or feedback?
Okay, I just want to say that I enjoyed it very much. I didn't attend all the talks, but whatever I attended was wonderful, highly educative. I would like to request that you have a consolidated mailing list, because last night I talked to people at Indore and they didn't know anything about it, although Sudipto was part of this earlier. But he apparently this year didn't get any mail. And one of the guys has in fact come back after a nice postdoc and has done something quite related to this. It would have been nice to have them participate here. The other thing I want to say is that, you know, this community is going to grow. So your selection has to be tighter per year. Maybe some other avenues have to be found, but I think alternate year is not a very good idea, in the sense that I think an invited talk in a national symposium once in 5 years is a pretty good scoring. I also don't see any logic in the parallel sessions, in the sense that there were places where I wanted to attend both. Okay. Now, being an outsider, my interests are somewhat peripheral, and my purpose was to learn what is happening in that business. So I don't really think that the present size justifies parallel sessions. We need to accommodate more people, maybe more poster session, more effective communication in posters, something like that. But you know, there are not very distinct themes in which one can separate the sessions. In the old days, if there was in the solid state physics symposium, there was a thermal physics session and there was a electrical properties session. They were quite independent of each other. In this business, they are not quite independent of, nothing is independent of the other. So it's hard to actually devise parallel sessions.
Yeah, so actually this parallel session, we had debated even 4 years back on whether to have it or not. Now, there are 2 reasons we went for parallel session. One is the obvious reason, is to accommodate more people. The second reason was that in a conference which encompasses a huge variety of topics, including, let's say, somewhat materials oriented stuff and somewhat esoteric theory, like, let's say, many-body localization or those kind of things, which are not yet completely in the realm of experimental testing right away.
Yeah.
So there, what happens is that if you keep the same session for everyone, then a section actually drops out. So it was essentially to have the entire audience engaged for the entire time.
Okay.
And to some extent, I think this year I was keeping a very close tab of the attendance in sessions. And I think the attendance in sessions in a way has been remarkable, because it has been 4 years, 4 days.
Yeah.
And 4 days, people have some tiredness that comes in, but yet the drop in the attendance has not been drastic. I think today last session, there was a slight lopsided attendance. One of the sessions was very well attended, the other was somewhat less attended, but this is a one-off.
Okay.
So this was the idea that we have, but of course, anything can be discussed.
Also, maybe one comment here is that when we started this meeting, we wanted this not to be a very specialized or a focused meeting, but a platform where, you know, anyone who is more or less doing condensed matter can come and give a talk as inclusive as we can be within whatever constraints, logistical constraints we have. Just before we go to HRK, maybe one more comment is that all the sessions are recorded and they'll be available on YouTube. So if you have missed something, let's say because you could not go to one parallel session or the other, you can find all of the talks on our channel in YouTube. They're recorded, and we will probably share a link once, in a couple of days or so on to all the participants. So let me go to then.
Just to add on to what Rajdeep said, the channel link is still live. Anybody can navigate to it at any point of time. Some of the speakers have requested their content to be edited out. So those particular sessions are not open for public viewing yet. Once they're removed, the rest of the sessions will be available. The otherwise, most of the sessions are online and you can always browse through and find. Some you may not find because probably they contain a particular talk which was requested to be removed. So, but they will be active in the next 3-4 days.
Yeah, once we remove and edit those, they will also be available. So may I then request Professor Krishnamurthy to say something?
HRK, are you with us? Okay. I'm not sure he's able to hear.
Yeah.
Okay.
Okay.
So anyone else?
I have one suggestion. I don't know whether it's relevant or not. These days, there are lots of candidates, the prospective faculty candidates are, those who are postdoc, they wants to come back to India. Is there any way we can adjust 3 or 4 postdocs, somehow we select them, 4 or 5 postdoc and give them 30 minutes opportunity.
Manoranjan, there were such people in this conference, without naming particular people. There were such people who gave talks.
Especially we should have some specific session only for them.
We did not put them up as a specific session saying they're trying to come back. But if you look at various sessions, there are people who are applying to different universities or institutes at the present time, who were, and we tried to accommodate as many of them as we could, as we got.
He is probably talking about 30-minute talks. So that's probably not the.
Yeah, so and specifically we designed one session. Specifically,
this is a zero-sum game because you will be, since you are not going to increase the size of the conference to 6 days, then you will basically not give the chance to certain faculties who are already there, because I don't think you can increase the number of talks too much above this.
Yeah,
now,
I
guess since we wanted to be as inclusive as we could, I think we have kept the policy that postdocs were mostly given 15-minute talks. But yeah, this is something for discussion which can be looked at the next conference.
Yeah, actually, we adopted an interesting formula that if we know that a postdoc has gotten an offer and is joining some Indian institute, he was considered a faculty.
Yes,
so let me not mention there were such cases here. But if a postdoc has not yet gotten an offer and is still doing a postdoc, then he was considered for the order.
Yeah, okay. This can be discussed. Thank you.
Yeah, sure. Any other questions or comments? Well, I don't see any other questions or comments. Then I would say, thank you to all of you. Of course, it's a community event and it's the community that makes it a success or a failure. And I hope we will keep coming together in the next year and years after that and have this platform where, we can try to gather as many people as we can. And basically, over a couple of years, maybe have a sense of what the community has been doing over the last 2 years, the whole of the community. With this, let me hand back to Pratap if you have some final words, parting words for the conference.
No, we have, I think, covered almost everything. So now we look forward for next year's session. And in between, the only parting comment is that if you have any comment, that any suggestion that comes to your mind later on,
yes,
just write to the same email address. That email account I will be handing over to the next organizers. So it will remain active and people will read the email. So just write in that email address. Thank you, everyone.
thank you, everyone. Then,
Okay, bye.
the end of the conference, and hope you all stay safe and